Today we're going to be computing a pretty lovely integral that should kind of break math, but doesn't quite do so. Let's roll. Okay guys, so today a beautiful integral that will probably break some math, honestly. So we're supposed to consider an integral from 1 up to infinity of the reciprocal of pi to the power of the floor of x with respect to x. What the hell? I mean, we are taking the reciprocal of pi, which is risen to the power of a function that's not even continuous. So, well, how the hell are we supposed to integrate it with respect to the variable that is inside of that function, which is, well, as I just said, not continuous? Oh man. I'd actually like to use some nice properties of this function that we have here in the floor of x, but first of all, what this floor of x even looks like. I mean, what this function even does. So the floor of x takes a number is given to the closest integer value that is below, or maybe it's equal to the number that is given. So if I took, let's say, the floor of 3.14, that will take me to 3. If I took the floor of 299, it's gonna get me to a 2. Awesome, stuff like this. It just takes me to the closest integer value that is below the number I'm given. Awesome. So now, well, how are we supposed to use this to evaluate an integral where we have like an infinite amount of values? It's gonna be, I don't know, are we going to multiply together like an infinite number of integers? It's probably gonna be 0 or something, but not quite. Well, let's just draw out a nice number line here, and let's maybe draw in some intervals, some integers I would like to mark here on this axis. So let's say 1, 2, 3, and 4. We know that on the interval between 1 and 2, so this interval right over here, this floor of x is going to be always equal to 1. I mean, on the interval between 1 and 2, but we're not taking in the value of 2 to that interval. Definitely not. Now, on the interval between 2 and 3, without taking in the 3, the floor of x is going to be always equal to a 2. Okay, that's nice, because, well, then if we go ahead and take the interval between 3 and 4, the floor of x there is going to be always equal to 3, apart from, well, the 4 that we are not even taking into the consideration of that in that interval. And we can actually go on and pretty lovely and generalize, I think, pretty lovely, saying that whenever x is in an interval between some a and a plus 1, where a is a natural number, we have that the floor of x will be equal to a, which is the bottom end, the lower bound of this interval. But absolutely whenever a is a natural number. No, actually an integer, but... yeah, actually an integer, but whatever, we only care about natural numbers here because we are integrating between 1 and positive infinity. Awesome, so we can go on and use this, but how? Like, how am I supposed to do it? You see, the nice thing is that we can rewrite this improper integral from 1 to infinity in a particular kind of a way. So we know that the improper integral from 1 up to infinity of, let's say, whatever, so just 1 over this pi of the floor of x up to, times dx is going to be equal to the limit as some kind of an n approaches infinity of, not the sum, of the integral from 1 up to n of 1 all over pi to the power of floor of x dx. But that's nice, because now we see that this n right here, it looks quite similarly to stuff we had right over here in this number line. I mean, what if we just went on and split the entire interval that we are calculating this integral on into just smaller sub-intervals that are all between natural numbers? Huh? Let's try and do it. So we can go on and rewrite this entire integral we've got right over here to get that is going to be equal to the limit, once again, as n approaches infinity of the sum from k being equal to 1 up to n of the integral from k up to k plus 1 of 1 over pi to the power of the floor of x with respect to x. But now, well, what is floor of x between k and k plus 1 where k is a natural number? It's k. And so this is just about going to be equal to the limit as n approaches infinity of the sum from k being equal to 1 up to n of the integral between k and k plus 1 of 1 all over pi to the power of k dx. But what's 1 over pi to the power of k with respect to x? Well, that's just a constant with respect to x. So we can, without a problem, go on and bring it here in front of this integral, getting that's going to be equal to, once again I have to rewrite this entire thing, so there's going to be a limit as n approaches infinity of the sum of k equal to 1, from k equal to 1 up to n, of 1 over pi to the power of k multiplied by the integral from k up to k plus 1 of 1 dx. Well, that's lovely, because what's the integral from k to k plus 1 of 1 dx? Well, that's just gonna be x evaluated from k to k plus 1, but that's just k plus 1 minus k, so that's just a 1. And so we get that we can, without a problem, go on and rewrite this entire thing as the limit as n approaches infinity of the sum of k, from k equal to 1 up to n of 1 over pi to the power of k, and this integral just becomes a 1 for every single k, so we can, just write it as multiplied by 1, but we can also not be doing that at all. Awesome, because, well, now we got rid of the integral. That's awesome, I think. Well, now the next thing is that here, this entire sum is just a geometric progression. That's basically a GP. And we have a formula for geometric progressions, because whenever we have a sum from k being equal to 1 up to n of, let's say, sum a to the power of k, that's going to be equal to a to the power of n plus 1 minus a all over a minus 1. So we can just go on and use this formula to get that this entire thing is going to be equal to the limit as n approaches infinity, on double O. Though, well, my infinity kind of looks like a double O, but let's just I don't know, assume that nobody cares about it. That's going to be the limit as n approaches infinity of, well, 1 all over pi to the power of n plus 1 minus 1 over pi, just 1 over pi, all over 1 over pi minus 1. And so we can just go on and multiply both sides, both the denominator and the numerator by a pi, getting that this entire thing, after also plugging in n, the infinity as n, is going to be equal to 1 all over pi minus 1, because, well, this thing is going to be just equal to 1 over pi to the power of n minus a 1 all over 1 minus a pi. Have a 1 minus pi to the power of n just going to approach 0 as n approaches infinity. That's just going to be negative 1 over 1 minus pi, so just multiply everything by negative 1 times negative 1, and you're going to get 1 over pi minus 1. And this is exactly what we got right here. This is our result. So we see, after all of those trials and tribulations, that pretty amazingly, the integral from 1 up to infinity of 1 divided by pi to the power of the floor of x dx is going to be equal to 1 all over pi minus 1, which some engineers would say is equal to a half. And so the integral from 1 up to infinity of 1 over pi to the power of the floor of x dx is equal to 1 over 2, is a half. yeah, I think some engineers are really happy. Yeah, they're happy that they serve right now. It's for you guys. You're engineers. Okay, so thank you guys for watching. I hope you enjoyed it, and see you in the next one. Bye.